Okay, welcome back to another video. Today we'll be talking about Gauss's law. Now, before we understand Gauss's law, I want to talk to you about electric flux. So let's look at electric flux first. So let's take an example of a rooftop. This is a house, and we have a rooftop. Now let's say it's raining. So let's say we have rain falling on the surface, right? So I can say the flux is equals to the area the raindrops are landing on times the rain droplets, right, that are dropping down. Think of it like that, right? If I have a lot of raindrops dropping down, right, that means the flux of rain is high, right? So you see, flux means a bunch of stuff passing through an area, just how rain passes through an area, right? Now remember, whenever we talk about flux, we're going to be talking about magnetic flux. You have already seen what magnetic flux is. We have seen magnetic flux. We're going to see electric flux. E. Both of these flux are basically area times the fields, magnetic field or electric field, right? And another thing you have to note is that the area and the, let's say, rain droplets are both 90 degrees to each other. They're perpendicular, right? So let's say the rain droplets, they are dropping at an angle. This is your rooftop again. We're seeing your rooftop, and they're dropping at an angle theta. So what's going to happen is, this is a raindrop. So what I'm going to do here is I'm going to take the cos theta. So I'm going to have flux is equals to area times the rain droplet cos theta. Make sense? If you remember in give me a second. If you remember in the magnetic flux, we had magnetic field times the area times the cosine of theta, right? In the same way, when we talk about electric flux, let's say there's a charge plus Q here, and I put, let's say, let's take a sphere, right? Sphere here, right? Now you see, from the positive charge, it will have an emanating field outwards, right? So it'll have an emanating field outwards, right? And those field lines, we can see these are the field lines. These are the electric field lines. Okay. So what's happening here is we have a positive charge. It has positive field lines emanating from it. And those field lines are, I've given you an example of a sphere or a circle, and those field lines are passing through the circle. And we know the area of the circle. So we can see the area of the circle times the electric field that is passing through this. So the electric field, right? This will give me the flux, the electric flux. So the electric flux is equals to the electric field passing through an area A. Now this could also be a square, right? And the electric field lines will pass through this, right? So what's the electric field that's the electric field lines, or the electric field that's passing through this certain area? The same way we saw the rooftop, the raindrops falling on the rooftop. So these raindrops can be said as the electric field or the magnetic field, okay? So if you see here, this is electric flux, right? Electric flux is equals to EA, where A is the perpendicular area, which makes the equation EA cosine of theta. I've discussed this. If your electric field or your area is at an angle theta, you're going to take the cosine to make the area and electric field both perpendicular. Now if you see in the example given here, we have the electric field which is passing through straight, and then we have the area at an angle theta. So what we do is we take E times A cosine of theta is equals to the electric flux. If you see this image and this example which I just explained to you, you can read it. It's the same thing what I just explained. Okay, so electric flux is extremely important because we're going to be understanding Gauss's law. To understand that, you have to understand electric flux. It's the same concept with magnetic flux as well. We saw magnetic flux is equals to B A cosine of theta, right? So this concept of flux is really intertwined in physics, and specifically electromagnetism, right? Electricity and magnetism are very intertwined with one another. You have to note that as well, right? Electricity and magnetism, or electromagnetism, right? So they both are very connected. Okay, anyways, so that brings me to Gauss's law. So what does Gauss's law says here? It says if an imaginary sphere is placed on a point charge with a point charge at the center of the sphere, then Gauss's law can be defined as EA equals to Q inside divided by epsilon naught. So what does Gauss's law really say, and what does it mean? Okay, let's understand it. So Gauss's law says, okay, let's say you have a charge here. It can be a positive charge, it can be a negative charge, whatever. Okay, we have a charge here. It can be positive Q, it can be negative Q. Okay, and let's say I draw an imaginary sphere outside of this positive point charge or spherical charge or whatever it may be. It has to be a charge. Okay, this sphere I draw it's an imaginary sphere. We call it the Gaussian surface. Okay, so what's gonna happen here is if I place any charge at this point, or if I can see any point here, right? Let's say I stand here, 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 right? You see, I'm at a distance r from this positive or negative charge. And if I send any position on this imaginary circle, the electric flux, right, which is equals to EA, right? Now carefully understand this. The electric flux at any point inside of this imaginary circle will be the same. Do you get it? I have a point charge at the center and I have an imaginary sphere. Any point I stand on this imaginary sphere, my electric flux will be the same. My electric flux will be the same. Okay? So electric field is going to be constant. Why, sir? Why will it be constant? Because you see, you're standing at the same distance, right? This distance is same, r. This distance is r. And this distance is r. So E is constant, right? Because the electric field is the same. Along with that, the area is also constant, right? Because what's happening here is you see here, this area is constant. It's not changing, right? It's the same area everywhere, right? The imaginary sphere that we have has the same area. Okay, so we have the magnetic flux, which is constant. Okay, so if you see back here, then we can see A is the Gaussian surface, and the area of that Gaussian surface is constant. Along with that, the electric field also is constant, right? If we see R1, right, at R1 we have E1 as the electric field. That electric field is constant. Along with that, the area is constant. Okay, so those two things you have to keep in mind. The area and electric field are constant. Okay, right, so you know that electric field is equals to KQ by R square, where K is equals to 1 over 4 pi epsilon naught. Okay, so can I write it like this? Q 4 pi epsilon naught r squared. If you notice here, this and this 4 pi r squared is just the area of the sphere. So you can say E is equals to Q A by E naught, right? And then I can move the A to the top, and it can be EA is equals to Q by E naught. And then we already studied just now, EA is electric flux. So electric flux is equals to Q by E naught. This is your formula for Gauss's law. Okay. So, okay, when Gauss did this, he didn't have any of this. He had this formula, but he had to prove it as well, right? So what Gauss did, he said, okay, my electric field is constant, my A is constant, so my electric flux is constant, right? The only thing, let's say this is a charge, this is the imaginary sphere. The only thing, let's say I'm standing here, he's standing here, right? I'm standing here, right? And I have E1 here, E1 here, E1 here, right? All E1 is the same. The only thing that can cause E1 to change is the charge here. If I make it plus 2Q, my E1 will change. If I make it plus 3Q, my E1 will change. So the only thing that can change my electric flux is the charge. Nothing else can change the electric flux. Because remember, the area of the imaginary sphere, it's a sphere, it's constant. The electric field is constant, and the only thing that can change it is the charge. So Gauss said that, okay, the electric flux is directly proportional to the charge. And then when he found the K constant here equals to KQ, he found that the K constant was 1 over E naught, right? So he found that, and he found this formula. Okay, I hope that makes sense. So here what happens is you get Q, the charge inside the enclosed Gaussian surface, divided by epsilon naught, which is the permittivity of free space, right? And what happens, sometimes we also have to take the integral, because sometimes we have area which is not exactly a sphere. We have areas for which we have to take integrals, right? But we're not going into that because your A-level spec doesn't have any of this, right? But in university you'll have to integrate it to find the area. Okay, so anyways, so this is Gauss's law. Okay, so let's look at this image here, where I've already explained the fact that the electric flux is equals to the charge that's inside the imaginary sphere and the epsilon divided by epsilon naught. So what we can say here is, let's say this, we have this sphere and it's inside a Gaussian surface. Now you see, I told you that epsilon naught is equals to EA, where E is constant because the electric field or the electric field line passing through every point is constant. Let's say 3 field lines, right? Field lines. Then at this point also it's going to be 3 field lines, right? So the electric field lines are constant everywhere. Okay, and the area is constant. You see this area is constant, so the area around the sphere is constant. Okay, right, so that's number one thing. The second thing I told you is that it's dependent upon charge. So what happens if we go from plus Q to plus 2Q? When we go to plus 2Q, what's going to happen is your electric flux will increase. So electric flux will increase as we go from plus Q to plus 2Q. Okay, so you see now we are having way more field lines. Think of the raindrops. There are way more raindrops, right? When there are way more raindrops, we say the rain is heavy. When they have less raindrops, we say, okay, the rain is less. In the same way, there are more raindrops here, right? So this means that the charge is more. There's plus 2Q charge, right? So there's more electric fields, so there's more electric flux, and that's because there's more charge. All right. Another concept I want to explain. Let's say we have the point charge here, and this is let's take this as the imaginary Gaussian surface, and then let's take this as the imaginary Gaussian surface. Would you agree if I say that this point and this point both will have the same electric flux? You would say no, sir. So this would be having more electric flux, this would be having less electric flux. But that's incorrect. Both points will have same electric flux. Now if you notice here, This is the first point and second point. Now you see the electric field gets weaker. So you see the field lines will be more here, right? And the field lines will be less here, right? So let's say this is point 1 and point 2. So we have electric flux at point 1 and electric flux at point 2, right? So we have B, not B, it's E1, A1, E2, A2, right? So let's compare the E1 values, E1 and A1, with E2 and A2. So you see at E2, my area of the sphere increases, right? Here we have a distance of R, and here we have R1, and here we have a distance of R2, where R2 is bigger, right? So area is bigger. So what's happening is the area in comparison to A1 is bigger. But the electric field is weaker. The field lines passing through a given area in the sphere is less. So the electric field is less. Hence, the electric flux remains constant. Okay, that's not the point. Keep that in mind. Alright, so we have a question from the IL specification, and this question is, it has some of the Gauss's law concept. That's why many students found this question challenging, but let's attempt it. So we have some spiders may be seen suddenly moving up into the air, even when there is no wind. This happens when they let out strands of web. The spiders are pulled upwards as electrically charged strands of web interact with the electric field of the earth. So they interact with the electric field of the earth. That's an important point. The average field strength of Earth's electric field is 120 volt per meter downwards. State with a reason the polarity of the charge on the strands. So what they've told you is that you have a spider, and the spider is moving upwards, and the Earth's magnetic field, electric field, I mean, is it's downwards, right? And we know the electric field always acts from a point of high potential to a point of low potential, right? Point of low potential. So it always acts from a point of a high potential to a point of low potential, which means if it is acting downwards, it's acting from a point of positive potential to a point of negative potential down here, right? And if the spider is moving up, let's say the strands were positive, right? That would mean that the spider would actually move down because the strands would be attracted to the negative, you can think of it as a negative plate of the earth. But instead it's moving up, so these strands must be negatively charged. So they repel, and it's moving upwards towards the positive charge with a force of Fe, right? And since it's, okay, this is a little extra point as well. So what's happening is it's losing its it's losing its EPE, and that EPE is being converted into half mv squared, because you see it is accelerating. We get the information later that it accelerates. When it accelerates, it has increased in velocity. So its electric potential energy is being converted into half mv squared, right? So yeah, so another question you might ask is, how is there a negative charge on these strands? Well, that's due to friction. Because of friction, there can be loss and gain of electrons, and due to that you can have positive and negative charge on these strands. Alright, so the answer to this question, you can write the polarity of the charge on the strand of web is going to be negative, because then it will repel the Earth's electric field and move upwards. Okay, that's the answer to this question. Okay, let's move on to the next question now. This says the spider is moving upwards after letting out a strand. So here I have the spider, it's moving upwards, and it has upward acceleration, positive acceleration. And I told you in the previous slide that we have a huge force of electric field, right, due to the electric field, because here it's negative and it's positive, it's attracting. Along with that, we know there's weight, right? So we can use Newton's second law, which is resultant force is equals to ma, and we can say ma is equals to Fe minus the weight. They've also given me the electric field, which is equals to 120 volt per meter. Okay, so let's understand it. I don't want to go too quick. So here's a spider. It's moving up because of the electric force. There's weight acting downwards. They want you to tell you the initial acceleration. right? Whenever they say initial, also ignore drag. So we're ignoring drag. And you know, whenever you were calculating acceleration from unit 1, that the resulting force is equals to ma. Ma is equals to Fe minus W, right? The upward force minus the downward force. Now what's going to happen is you know that E is equals to Fq, where Q is the charge on whom the force is acting upon in the electric field. And we know F is equals to EQ. So instead of writing Fe, I can replace it with, and substitute it with EQ minus mg is equals to ma. Then at last I can say A is equals to EQ minus mg divided by m. And this is my final formula that I get. Now you can just easily input all the values and find one answer. So we have E as 120 times the charge is 3 times 10 to the power of negative 7 minus the mass, which is 3 times 10 to the power of negative 6 times 9.81 divided by 3 times 10 to the power of negative 6. So you get the answer, and just give me a second. You get an answer of 2.19 meter per second square. So here we have the next question, and this is what I'm talking about as the Gauss's law. That it's connected to Gauss's law. So what they want you to find is, you can see that Earth has an electric field because the charge is distributed all over its surface. Determine the quantity of charge on 1 meter square of Earth's surface, which would cause an electric field of 120 volts per meter. You should assume the charge is evenly distributed. So you can understand, connected with Gauss's law, you have the point charge at the center, and you have an imaginary surface here, right? Imaginary surface here, a second, right? Here we have the imaginary surface. So what's going to happen here is, this imaginary surface is at a distance of r, and this imaginary surface is actually the Earth they've given you. And how do I know it's an imaginary surface, and how do I know that all of this information is because they said the charge is distributed evenly, right? That would mean that it's a sphere that's at a distance r from the point charge at the center, right? From the point charge at the center Q, right? Okay, so now what I can do is I can find the charge that's there due to Q. Like, what is the charge Q, right? I can find that charge. Okay, how can I find that charge? Okay, I can do is, right, so here we have the formula, right? And I have to find this charge Q here, right? So this charge Q will be evenly distributed, right? Will be evenly distributed over this area, right? This charge Q will be evenly distributed over this area, okay? So this charge Q will be evenly distributed over this area, so I have to find how much charge would there be in 1 meter square. I hope you get the question now, okay? So what we can do here is we can find this charge that's inside of this Gaussian surface as EA Q in the charge inside E naught. So what I'm going to get here is, I know A is equals to, E is equals to 4 pi r square times E naught is going to give me Q inside. So let's find this Q inside. I have 120 times 4 pi times 6400 times 10 to the power of 3 is equals to, and times, the epsilon naught, which is going to be, I think, 8.85 times 10 to the power of negative 12. Let me just verify that. Right, so you will get the electric field as, let's find it out, the E naught value is correct, 3 times 8.5 negative 12. Wait, I forgot to square it. 1 second. Square. Yeah, so it's going to be 546,631 coulombs. Yeah. So this is so most students, they would write this, and then what they would do is then we would divide it by 546,631, divide by 4 pi r squared, and that will give you the final answer, right? But there's an easier way to do this, and I felt that I did the way that's a bit longer. So what I would have done instead of this is, you would have gotten 5 4 6 6 3 1, and this is in 4 pi 6400 times 10 to the power of 3 square. So what would it be in 1 meter square? X. You cross multiply, you can get the answer very easily, right? But this is a longer way. The easier way, that's why I made you derive the Gauss's law, right, is the electric flux is equals to charge inside divided by E naught, right? So what you can do is give me a second, is I made you guys put 4 pi r square, right? So that was what that meant, was the amount of charge in all of the sphere. But instead of 4 pi r square, you can just put 1. So you will get the charge in 1 meter square. That's it. So then what you can do is you will get E1 times E naught is equals to charge inside. You just multiply 120, which they give you, times with the epsilon naught value 8.85 times 10 to the power of negative 12, and you will get the answer straight up as 1 point. Give me a second. I found the answer as 1.062 times 10 to the power of negative 9 coulombs. And if you divide both of these answers, cross multiply and divide them, you can get still the same answer, which would be a second, which would be 1.062 times 10 to the power of negative 9. So you see, both of the answers are same, but the approach I went with first was very long, and this is a very quick one, right? So the reason I made you understand Gauss's law is so you could have the easier approach, and then I went with the longer one. Okay, so you go with the easier approach, so you have to understand how to use the formula. Okay, so we found the amount of charge in 1 meter square, and we can just put 1 here. If you want to find in 10 meter square, just put 10 here. 20 meter square, 20 here. The entire surface, you can put this formula inside here if you want to find for the entire imaginary surface, right? So that's up to you. So if you want to find for the entire imaginary surface, you can put the whole area. For 1 meter square, you can put 1 meter square here, right? So I really want you guys to understand this question, because physics with understanding is beautiful, and that was Gauss's law. And that's it.